Welcome back. Today, we're diving into something called transducer adaptation. Now, it sounds a bit technical, but really, it's about a fascinating piece of biological engineering that solves a huge problem: how our balance sensors avoid getting stuck.
All right, let's get right into it. We're going to look at how your vestibular hair cells, those tiny little sensors that handle your balance, can stay so incredibly sensitive, even with the constant, massive force of gravity pulling down on them all the time.
So, this brings us to a central challenge for our vestibular system, what we call the saturation problem. It's a real engineering puzzle that nature had to solve.
Yeah, think about it for a second. Gravity isn't a small force, it's huge, and it's always there. So why don't our balance sensors just get stuck in the on position? I mean, if you kept pushing on any normal sensor, it would just max out its signal, right? It'd become totally saturated. And that's exactly the problem our hair cells have to solve if they're going to have any hope of picking up on the really small, fast movements that actually matter for keeping us upright.
So how does the body solve this? Well, nature's solution is this really elegant process called adaptation. You can think of it as a sophisticated, built-in reset button for the sensor.
What it does is actively and continuously reset the hair cell's operating point. This stops it from saturating and, crucially, keeps it super sensitive to any new movements. The analogy of recentering a microphone to hear a whisper in a loud room was perfect. Adaptation is what keeps our balance system in that sweet spot, always ready to go.
Now here's where it gets really cool. This isn't just one single process. It's actually a team effort. You've got two different players here, a really fast one that works in milliseconds and a slightly slower one that takes tens of milliseconds. They have different jobs, so let's break down what each one does.
First up, let's talk about fast adaptation. This is the hair cell's immediate, rapid-fire response, happening quicker than a blink of an eye.
Okay, so when a force, like a head movement, opens up these things called MET channels, calcium ions just flood into the cell. But here's the genius part. That calcium doesn't just send a signal to the brain, it immediately turns around and acts on the channel it just came through, telling it to calm down and reducing the chance it'll stay open. It's a perfect, self-regulating, negative feedback loop.
So it's this super simple but elegant three-step dance, right? 1. Channels open. 2. Calcium rushes in. 3. That very same calcium acts as a brake, binding to the channel and telling it to ease up. The result? The cell becomes incredibly good at sensing changes in force, not just the steady force itself. It's all about detecting the new stuff.
And this is where it really matters for us in the clinic. This whole fast adaptation thing is absolutely crucial for our ability to detect those quick, high-frequency head movements. You know, the exact kind of thing we're testing for with the video head impulse test, or VHIT. This is the physiology behind that test.
Okay, so that's the fast system. Now let's shift gears and look at the second mechanism. It's a bit slower, but no less important. This is slow adaptation.
This one is more, well, mechanical. It involves a tiny molecular motor called Myosin 1C. And what it does is physically move. Imagine a little climber on a rope. This motor basically slides down the internal structure of the stereocilium, which releases the tension on the gate, the tip link, and that resets the whole system.
So let's say you're just tilting your head to one side and holding it there. That's a sustained deflection. This myosin motor kicks in, slips down, and eases the tension. This prevents that static head tilt from just locking the whole system up in saturation. It actually allows the channel to close and reset, even though the hair bundle itself is still physically bent.
And again, this has some really fascinating clinical implications. If this myosin motor system isn't working right, it might help explain why some of our patients report those persistent static symptoms. You know, that constant feeling of being tilted or just being unsteady, even when they're standing perfectly still. So you can see how understanding these two separate mechanisms, the fast and the slow, really gives us a great framework for thinking about and interpreting our patients' symptoms. It helps us differentiate between static and dynamic problems.
It really spells it out, doesn't it? If you have a problem with that fast, calcium-driven adaptation, it's more likely to show up as a dynamic dysfunction, something you'd pick up on with a test like VHIT. But if the problem is with the slower myosin motor adaptation, you might see more of a static dysfunction, like issues with just holding a certain posture.
All right, let's bring it all together. Here are the key takeaways from all this. First, fast adaptation. That's the calcium one. It happens in milliseconds, and it's all about sharpening our sensitivity to dynamic changes. Second, slow adaptation, the myosin motor, takes a bit longer and its job is to compensate for static forces like gravity. And third, and this is the big one, both of them work together to keep the hair cell in its sweet spot, its optimal operating range, so it can do its job.
So we've covered the ins and outs of fast and slow transducer adaptation. Next time, in Video 8, we're going to dive into the difference between type 1 and type 2 hair cells. We'll find out how their unique ion channels basically act as temporal filters, something that's absolutely critical for the lightning-fast demands of our balance reflexes.
Thank you so much for listening. To explore more on dizziness, vertigo, and imbalance, or to find some great resources for both clinicians and patients, please head over to AustralianDizzinessClinics.com. And of course, we'd love it if you'd subscribe and leave a rating.